Hello, everybody. Welcome back to Linear Algebra. Say hi if you're here. I see Navik's already here. Good morning, Navik. Yeah, I looked that up. The Humble Bundle Applied Math Productivity. Looks neat. Good morning, Taylor. Hello. I'm not sure who said evening from China, but hello. Good morning, Emma. We'll get started in, I don't know, a minute or so. Hopefully a few more of you trickle in. Good morning, Shutong. Glad you're here. Oh, it's Chow. Nice to see you, Chow. I think Google Translate might be a little bit wrong on that one, Navik. Okay. Well, it's 9 o'clock, so we could get started. Oh, looks like Suba's in the chat, just in time for the simultaneous sip. So if you have your coffee or your water or your tea, or whatever you may have, feel free to join me in the simultaneous sip. All right, let me see in the chat who joined in on the sip this morning. But the plan for today and basically the rest of this week is we're going to keep working on this inner product space section. Okay, so I know yesterday's class was a little bit theoretical. So today we'll see some more examples of how we're going to use these concepts. But slow me down if I'm going too fast. We have not a ton of material left for this semester, but we still have, 5 classes. So slow me down if we're going too fast. All right, nice. We got a few people joined in with the SIP today. Excellent. All right. Okay, so we said at the end of class yesterday we could use these inner products to define a length. So just some more definition. A unit vector is one whose length is 1. So it's a vector not in the column vector sense, but in the more the theoretical vector space sense. So we'll see, like, if a polynomial's length is 1, we call it a unit vector. Right, so if we take the inner product with itself and we get 1, then we have a unit vector. And just like before, the distance between two vectors is the length of u minus v. But here again, we're going to be using length in terms of our inner products. And then just one last bit. Vectors u and v are orthogonal. Okay, what do we think how do we think we test to see if two vectors are orthogonal? Let me know in the chat. So two vectors u and v are orthogonal if, yeah, see, chat, you'd want to say the dot product, but we're talking about the inner product now. But yeah, Taylor, you're right. So if their inner product is 0, right? Because we don't really know what it means to take the dot product of two polynomials, for instance. But we'll use this term orthogonal, just to mean that their dot product or their inner product is 0. Okay, let's look at an example. So we'll let P2 have the inner product we'll let PQ have the following inner product. So this is the one we looked at yesterday. P of 0 times Q of 0 plus P of 1/2 times Q of 1/2 plus P of 1 times Q of 1. The question is compute the lengths of P of t, which is equal to 12t squared, Q of t, which I think we already did yesterday, but do it again, which is 2t minus 1, and P minus Q of t. So this is really going to ask us how close are these two polynomials in this in the sense of this inner product. Okay, so I'll give you let's say a minute and a half or so to try to work this out. Does somebody in the chat want to say how they're going to compute these lengths? And if you get an answer, feel free to share it with the chat. All right. Oh, Taylor said something. For p minus q, do we have to do p minus q dotted with itself? Yeah, so we would have to figure out what is the polynomial. What is the polynomial p minus q? So that would just be 12t squared minus 2t plus 1, right? Because we subtract this whole thing. And then yeah, take the dot product, or take the inner take the inner product with itself, and then take the square root of that inner product. Okay. So to find the length of these vectors, the length of p is equal to the square root of p with itself. Which is equal to p of 0 squared plus p of 1/2 squared plus p of 1 squared. P of 0 is 0. P of 1/2 is 3. And P of 1 is 12. So 0 plus 9 plus 144 is 153. And I guess we should be taking the square root of all of this. So let's correct this. And so if the magnitude squared is 153, the magnitude of P is the square root of 153. Right. Similarly for the magnitude of Q squared, which is Q inner product with itself. When we do this, we get -1 squared plus 0 squared plus 1 squared, which is 2. So the magnitude of Q is the square root of 2. And then last, P minus Q is the polynomial 12t squared minus 2t plus 1. I guess to evaluate its inner product, we need to evaluate it at 0, 1/2, and 1. And so its magnitude is equal to the square root of 1 plus 9 plus 121, which is equal to the square root of 131. So in the sense of this inner product, the distance between the polynomials P and Q is the square root of 131. So can I get a little feedback from you all in the chat? Whether this idea of finding the length of a polynomial given an inner product is one that you understand, or maybe you need a little bit more clarity for. All right, a couple of thumbs ups. All right, that's good. That's good. You know, and given a different inner product, maybe these polynomials would have a different length. We'll see some applications where you're given, you know, let's say you're in the lab and you want to find the line of best fit or the curve of best fit, and you're given some data points. That would be this information here. And you want to ask, you know, which polynomial matches this data the best? You'd want to minimize some sort of distance here. We're going to talk about how to do that in a second. But this stuff has applications in you know, the field of data science or statistics. That's pretty useful. So we'll take a look at that hopefully in a few days. Okay, so let's talk about that a little. So a common problem in applied math involves a vector space V whose elements are functions. Maybe not polynomials, but continuous functions or just functions. The typical problem you'll try to solve so the problem is to approximate a function f in V by a function g in some subspace. Okay, so before we write any more, basically we're given some function f, and we have a subspace that we particularly like for instance, polynomials. And we want to ask which polynomial is most like f. Okay, you've actually seen this before if you've taken Calc 2. At least at NC State we taught this. So let me see in the chat. Have you done like Taylor expansion or Maclaurin series, Taylor or Maclaurin series when you took Calc 2? Is that familiar? At least you've heard of it before? Yeah, it was the last chapter. Yeah, so that's kind of the idea what you're doing. You have a function and you're approximating it with a polynomial. And in calculus, you had some kind of procedure to find that polynomial. But maybe we're going to deal with an inner product that's a little different. So our procedure will be slightly different, but if we restrict it the appropriate way, we could get back that Taylor series. Okay, so that's kind of the idea. Okay, so we're going to consider the case where the length of the distance, so how far away f and g are, is determined by an inner product. You know, in the case of the Taylor and Maclaurin series, it was determined by like matching the derivatives, had derivatives and first derivative, second derivative, third derivative, all had to match at a certain value. Here we're going to say that it's determined by some inner product. And what we'll see is in this case, the best approximation of f by a function in W the way we best approximate f by a function in W is we're going to take f and project it onto W. All right, so what we did in our last section, orthogonal projections, it's going to appear again, but now in this, not in the sense of column vectors, but in the sense of, you know, a general vector, a general vector space. Okay, so let's take a look at an example to see that what we're doing here is really not too bad. Okay, so this example has two parts. So we'll just do one part at a time. Okay, so we'll start by saying let V equal P4. We're going to need some more space. So with the inner product defined by PQ is equal to P of -2, Q of -2, plus P of -1, Q of -1, plus P of 0, Q of 0, plus P of 1, Q of 1, plus P of 2, Q of 2. Okay, so that's our inner product. We got to evaluate our polynomials at -2, -1, 0, 1, and 2, and multiply them together like this. So we'll let P1 of t equal the polynomial 1. Right, this is in P4 because its degree is 0, and P4 is polynomials of degree at most 4. We'll let P1 of t equal t. And we'll let P2 of t equal t squared minus 2. Okay, and so the question is, show that, okay, P1, let's make sure we did this right. This is P0. I'm not sure why I labeled them like this. Sorry, P0 is 1, P1 of t is t, and P2 of t is t squared minus 2. Show that P0, P1, P2 is an orthogonal basis. Sorry, is an orthogonal basis of the subspace P2. All right, so that's the first part of the question. I'm not going to write the second part yet. All right, so we have these 3 polynomials. How do we show that? So this is for the chat. How do we show that P0, P1, and P2 is an orthogonal set, right? Because we need to show it's an orthogonal set that spans all of P2 to show it's a basis. So how do we show it's an orthogonal set with respect to this inner product? Yeah, that's right, Taylor. So we want to evaluate the inner product of P0 and P1, and let's hope we get 0. Let's take the inner product of P0 and P2, and we should get 0, and the inner product of P1 and P2. And again, we should get 0. Okay, and then the question is, so once you show that, then the question is, how do we know that this is a basis of P2? Sorry, the span. How do we know that the span of this set is P2? Or how do we know that this set is a basis for P2? Would anybody like a little bit more time to work on this, or are we good for me to get started? I'm fine giving more time if you need it. All right, I'll start working this through. Let's start with P0 times P1. So P0 is always 1. So all these terms in our inner product that come from the first term is just 1, 1, 1, 1, 1. And P1 is the polynomial t. So it'd just be -2, -1, 0, 1, and 2. And when you add all those up, you get 0. Okay, now we'll do P0 times P2. T squared minus 2 evaluated at -2 is 2. T squared minus 2 evaluated at -1 is -1. T squared minus 2 evaluated at 0 is -2. This is an even function, so it works out to be this. 2 minus 1 minus 2 minus 1 plus 2. That's 0. And then P1 times P2. Well, this is P1 evaluated at -2, and this is P2 evaluated at -2. So it's -2 times 2 plus -1 times -1 plus 0 times -2 plus 1 times -1 plus 2 times 2. -4 plus 4 cancels. 1 minus 1 cancels, and that's 0. So this is all 0. Okay, so we showed it's an orthogonal set. How do we know it's a basis for P2? It's linearly independent. That's true, but like for instance, P0 and P1 is also linearly independent. So what else? Well, maybe you'd have to look back in your notes a little. It's that there's 3 of them, right? And the dimension of P2 is 3. So any 3 linearly independent polynomials in P2 span P2. Is a basis for P2. So we know that P0, P1, P2 is a basis for P2 because any 3 linearly independent in P2. So because any 3 linearly independent polynomials in P2 is a basis for P2. Right, and that's because of the dimension. The dimension of, right, P2, we said that P2 and R3 are basically the same vector space. So their dimension is 3. So yeah, so since we showed we had an orthogonal set, we had a theorem that said all orthogonal sets are linearly independent. And Since there's 3 of them, it must be a basis for P2. Right, and that's and we also have to be careful. We have to make sure that each of these live inside of P2, and they do, right? This polynomial has degree 2, this one has degree 1, and this has degree 0. Okay, so that's the first part of the question. So now that we have an orthogonal set, it makes sense to do an orthogonal projection. So find the best approximation to the polynomial So find the best approximation for the polynomial 5 minus 1/2 t to the 4th. Okay, so this is a degree 4 polynomial, and we want to approximate it by degree 2 polynomials. Okay, so how are we going to do this? Yeah, you're on the right track, Chow. We want to not find the least square solution, but we just want to find the orthogonal projection. So it's the same idea. The least square solution would tell us like the coefficients of P0, P1, and P2, that's one way to solve it. But we could just find the orthogonal projection. So we'll call that P hat. And the way we get the orthogonal projection is exactly the same as how we did it with column vectors. It's P times P0 over P0 times P0 times the polynomial P0 plus P times P1 over P1 times P1 times the polynomial P1 plus P times P2 over P2 times P2 times the polynomial P2. Okay, and so when we work this out, this polynomial, it's going to end up with a degree 2 polynomial, maybe it's less than 2, it will be as close as possible to this degree 4 polynomial using this inner product. Okay, so I'll give you a few minutes to try to work out these calculations, and then we could do it together. And when I say together, I mean I will just do it and you guys will watch. Please ask any questions if you need something to be clarified. All right, so we need to find P times P0, P times P1, P times P2, and then each of the basis vectors times itself. So I'll just work out these calculations. So we evaluate our polynomial at -2. We evaluate it at -1. We evaluate it at 0. We evaluate it at +1 and at +2, and add all of them up. And you get 14 minus 6 is 8. So these coefficients are going to be the same for all of them. And so when you add these up, you get 0. All right, when you work all this out, you get, let's see, -6 minus 9, -31. Is that true? Yeah. So -12 minus 9 minus 10. Okay, so now we have to compute P0 times itself. Right, because that just gave us the numerators here. We also have to compute the denominators. P0 times itself is just 1 squared plus 1 squared plus 1 squared plus 1 squared plus 1 squared, which is equal to 5. We don't need to compute P1 times itself because we already know that this term is 0. We could do it anyway, just for practice. So 4 plus 1 plus 0 plus 1 plus 4, that's 10. And then P2 times itself is 2 squared plus negative 1 squared plus negative 2 squared plus negative 1 squared plus 2 squared, which is 14. Okay, so we did it. Our approximation, which we could call p hat, is equal to 8/5 times p0, which is the polynomial 1, plus 0/10 p1, plus negative 31/14 times the polynomial t squared minus 2. Okay, so this polynomial is closest in the sense of this inner product to this polynomial 5 minus 1/2 t to the 4th. So this is the closest degree 2 polynomial to this degree 4 polynomial in the sense of this inner product. I know this question had a lot of computation to it, but this is identical to what we've been doing last week. This idea of orthogonal projection. Just because we have a different vector space and a different inner product doesn't mean our concepts of orthogonal projection don't work anymore. Does anybody have any thoughts or feelings that they would like to share with the class about this question? You know, it could be as simple as a thumbs up or a thumbs down. Taylor's happy with the question. That's good to see. All right, I can't do it now because we're using a webcam, but we could plot this with Desmos, and you could see that it's going to have similar shape to 5 minus 1/2 t squared. And in fact, it's going to be closest when we're at the values 2, -1, -2, -1, 0, nice cruise, 1 and 2. So at those 5 values that we evaluate our function at, it's going to be a pretty good match. Okay, well, I think this is a good place to stop for today. Tomorrow we'll start class with a couple of proofs. So if you like proofs, that's great. We'll get some practice with those. If you don't like proofs, well, maybe you'll like them after class tomorrow because they're neat. These ones we're going to do. All right, so make sure to hit the like button before you get out of here. As my friend Navik says, it's so important. Smash the like button. But I'll stay around to answer any questions. But if not, get your homework done. It's due tonight in, 14 hours. But it should not take you that long. It's a quick one. So, yeah. Get started on it and send me an email if you have any questions about it. Yes, smash the like button. We're 3/4 of the way. 3/4 of the way to 1,000 subscribers. Can you believe it? They said it couldn't be done. All right, well, if there's no last minute questions, I'm going to end the stream. Bye-bye.